final step in the process might just be the most dramatic. That's taking those small bits of beryllium and aluminum hydroxide gels and burning them at high temperature to drive off that hydroxide so that we have aluminum and beryllium oxide. And then we pack that material into small metal cathodes that go to the accelerator facilities. This last step will take the beryllium and aluminum pellets that we created in the previous video after they're dry and put them in a form that is usable by the AMS for analysis. This step involves creating beryllium oxide, which is toxic, and aluminum oxide, which is not. It also involves working with an open flame or a very high temperature furnace, and as such could easily contaminate the laboratory with beryllium oxide if it's not handled carefully. Accordingly, this step is only performed by laboratory staff, not by students. In order to proceed, we transfer the pellet to a new hand-blown pure quartz vial. We use stainless steel funnels that we have designed for this purpose. One end fits into the centrifuge tube snugly, and the other end fits into the quartz vial. All we then have to do is invert, and the pellet falls into the quartz vial. The first part of the process involves converting the hydroxide pellets to oxide form. We do this by burning the samples over a torch or in a furnace at high heat. This is a hazardous process and it needs to be done with care. Next, we add a small amount of powdered metal to each sample. This helps dissipate the heat from the material when it's on the AMS in a vacuum and results in increased beam currents, leading to more precise analyses. This metal is usually niobium, but occasionally some accelerators prefer silver. Depending on which AMS lab the samples are going to, we need to decide which metal to mix our sample with. We do the addition of the metal using a small scoop so that we have a consistent amount of metal added to each sample. So we start with samples that are in quartz vials. They have lids on them to protect them, and these samples have just come out of the furnace where they have been oxidized. They're in a black metal rack and they're in quartz crucibles. Next, move to the left where you'll see cathode funnels with tampers at the rear part of our sample holder. Each one of those cathode funnels has a tamper slipped inside it, and those will be used to transfer the powders from the samples in the quartz vials into the cathodes. Further forward, you'll see a row of cathodes ready to be packed. They're inside Nalgene cryo vials, and each cathode is labeled as is the cryo vial. You'll notice that the sample holder or packing plate is labeled with the letters A through L that correspond to the samples. In front of the packing plate or sample holder is a cathode holder, metal and aluminum. It has a nib on it onto which the cathode, which you can barely see under Lee's hand, slips. And then there's a tamper that is used with a hammer to pack the material from the samples in the quartz vials into those cathodes. As you move toward the right of the fume hood, you'll see a bottle of ethyl alcohol that's used for cleaning if we have any spills. And then there are 3 bottles for dirty materials. We have a bottle for dirty tampers. We have a bottle for dirty tube funnels that were used to move the samples from the test tubes where they were dried into pellets into the little quartz vials. And then you'll finally see a dirty bottle for cathode funnels. Those are the funnels that slip over the cathodes. You can see those cathode funnels at the back of the sample holder. And they're used one at a time for each sample, and then they're placed in the dirty funnel bottle. After adding the metal, we need to homogenize the sample. Very carefully and slowly, we use a metal tamper, it's a drill bit blank, to gently break apart the beryllium or aluminum pellet and mix it with the powdered metal. Our goal is to create a completely homogeneous powder. This takes some patience and some practice. Once the powder is homogenized, we use a different stainless steel funnel to transfer it into the cathode. A small piece of metal in which the sample resides goes into the sample changer in the AMS. Finally, we pack the powder down into the hole at the top of the cathode. We use a metal tamper to help scrape all of the powder into the hole, and then use a hammer to compress it. We want to create a flat, even surface, which will ultimately be sputtered by a beam of cesium at the accelerator. More consistently packed cathodes will lead to better and more consistent analytical performance. The sample is now ready for AMS analysis. We work with many different AMS labs around the world, predominantly those in California and Indiana. That would be Livermore and Prime Lab. But we also measure samples with the accelerators in Scotland, Australia, and South Africa. Each AMS lab uses a slightly different cathode, so your samples may not look exactly like those you'll see in this video. We send the samples to the AMS, where they're analyzed in reference to a series of standards. The AMS quantifies a ratio of the counts of the rare isotope in relation to the current generated by the more abundant stable isotope. The wait for AMS results can take anywhere from several weeks to several months. The wait's out of our control and depends on the facility schedules and maintenance of the accelerators. When your data are returned, we'll help you with the calculations that turn the measured isotopic ratios into cosmogenic nuclide concentrations and ultimately into what you really care about, ages or erosion rates. Cathode packing summary. We convert beryllium and aluminum hydroxide pellets to oxides, a form that is usable by the AMS. We do this conversion by burning the samples over a torch or in a furnace at high heat. We then transfer each pellet to a quartz glass vial using a funnel to minimize sample loss, and we add metal powder. We homogenize each sample, making sure not to spill any of the beryllium oxide because it is particularly toxic. Once the powder is homogenized, we use a different stainless steel funnel to transfer it into a small hole at the top of the AMS cathode. Finally, we pack the powder down into the hole at the top of the cathode. The sample is now ready for AMS analysis.